Now, to analyze this very complicated system, there are a number of steps that we are going to take, approaches that we will be following, though we may not do them necessarily in the order that I list them here. And what these approaches should be, really, we were exposed to when we thought about the simple harmonic oscillator. That too was a fairly complicated equation. It was only in one dimension, but we had built up a very general set of methods that allowed us to analyze that system. And we will be doing some of the same things here. So for example, at some point we most definitely will be going to find the natural units or for this problem. We'll be working in natural units, equivalently carrying out some kind of a dimensional analysis. And that would further simplify our problem by at least removing all of these various constants that we're seeing here. We're not going to do that quite yet for a number of reasons. For the harmonic oscillator, it was very important that we did this right off the bat so that we could expose this position momentum symmetry. We don't have anything like that here, so it's not quite on our critical path quite yet. Later on, we will do it, but for now, we'll just suffer a bit through writing down all of the constants, but we will eventually do that. If you think back to the harmonic oscillator, another thing that we had really worked pretty hard on was to look at the symmetries of the problem, right? And symmetry, as we are learning, really plays a very important role in quantum mechanics. It frequently can radically simplify our quest for finding the bound states of a given Hamiltonian. So we definitely are going to be putting a lot of emphasis on symmetry as well as the natural units. Now, a third thing that might occur to you when you look at this equation is to think, well, look at this. I've got a radius r. I have my del squared. Very likely I want to try to handle this kind of thing in some kind of spherical coordinates. And that is definitely something very true, and that's something we will be moving toward. And actually, if you think carefully about it, this spherical coordinate idea has to be intimately tied up with the symmetry idea. After all, the reason why we're thinking of spherical coordinates is not just that I have a radius r here. I mean, after all, I could have an equation written down in all kinds of different complicated interactions, and I could still just transform it to spherical coordinates. What makes it useful to do so is that this Hamiltonian actually has what is called spherical symmetry, right? If I were to rotate my coordinate axes, I know this Hamiltonian has to take back its original form, right? It doesn't matter for the Hamiltonian, how I choose my x, y, and z coordinate systems in terms of rotating those systems around. So these two here are really very closely coordinated with each other. Now, another approach that we could take, and we're actually going to be combining all of these at various stages, to solving now what is a very complicated now partial differential equation. It's no longer even an ordinary differential equation. It's a very powerful method called the separation of variables, which allows us to transform partial differential equations into ordinary differential equations. But what we're going to see is, once again, symmetry is going to play a key role in allowing us to carry out the separation of variables actually in a very natural way. So the natural units are something we can do at any time. Spherical coordinates are really a reflection of the fact that we have this rotational symmetry in our system. And also the separation of variables is going to be aided by looking at the symmetry. So the first thing I think we really would want to look at is to try to really think through the implication of symmetries for this particular problem.